Hey Honors Chem, I just wanted to do a video on cell potentials and voltage for electrochemical cells. Last time we talked about redox and said that these things can gain electrons and lose electrons, and now we're going to take a look at what we can do with the energy produced from that gain or loss of electrons, things like batteries and electroplating. So your book and I are going to use these three things pretty much interchangeably. The electrochemical cell is a cell we set up with two different metals or two different substances that will gain and lose electrons, and we're going to talk about the electrical potential generated from that. So electrical potential is measured in voltage, so if your book says calculate voltage, calculate cell potential, calculate E cell, that's what we're talking about here. There's also one other notation they're going to use. They're going to have an aught, a little superscript 0, and that stands for standard conditions. So standard conditions are going to apply in electrochem. We'll see that in thermochem next chapter. It's 25 degrees Celsius, 1 molarity, atmospheric pressure, normal conditions. So if we don't have normal conditions, then we'll have to do something else. So you know that metals are losers of electrons. Some are better losers than others, so we have a certain voltage associated with each. And these are called standard reduction potentials. It's the voltage given off when these things are reduced. So the standard reduction potentials are listed in the back of your textbook in Appendix 35 through 37. You don't have to do a lot of math, you just have to add together two numbers. You just have to find the right two numbers. So you know that it's redox, we have reduction and oxidation, but these are all listed as reductions. So you're going to have to flip one. So let's pick two metals. Actually, I had my wife pick two metals. She picked copper and iron. So we're going to use those two to set up a hypothetical cell. Careful with these because both of them have different oxidation states. I chose the +2 version of each. So these are the reduction reactions for each of these metals. Excuse me. Because they're both listed as reductions, we know that one of these is going to have to be reversed. So we'll look in the back of the book and get our reduction potentials. For the iron reduction reaction, it's negative 0.44 volts. For the copper, it's positive 0.337 volts. So the negative would be energy given off, voltage given off, and we know that iron is more reactive than copper, so you get a larger negative value for iron. So if you look at the reduction potential list, your alkali metals are the very bottom of the list, the largest negative values, because lithium and sodium are by far the best losing metals. So we know that this isn't going to happen. You're not going to get iron that's oxidized to naturally go to iron in its free state. The reverse is more likely to happen, and that's why this has a negative value. Alkali metals don't reduce automatically. It takes a lot of energy to make that happen. So if we're putting together these two metals, iron is the more reactive. It's the one that will be preferentially oxidized. So that will also give us an overall positive value. So we're going to flip this one because we know these are both written as reductions. They can't both be reduced. It's one reduction, one oxidation. So could just flip the arrow, but then it doesn't really look quite right, so I'm just going to rewrite it here. Okay, so oil rig, oxidation is loss, reduction is gain. Because I flipped this, I'm going to change the sign of my reduction potential. So the math is really easy. We just add them together. This overall reaction will have a voltage of positive 0.777 volts. Okay, we can sum it together then. In our overall reaction, the iron is being oxidized, the copper is being reduced. We write it as half reactions to make it look better, but this is the overall what's going on. Because it is positive, that means this reaction will happen spontaneously. It will happen without outside influences. We don't have to supply electricity for it to happen. It will supply 0.777 volts that we can use for whatever. So this is basically how you set up a battery. You get different metals, allow ions to flow between them. That's your transfer of charge. And then you connect it with a wire to the different terminals, and you can use that electrical potential for whatever you want. Different batteries use different solutions and different metals. If this is a negative value, so if we were to do the reverse reaction, the reverse reaction would have a negative cell potential, which means that's how much electricity you would have to put into the system to get the reverse reaction to happen. So we do that sometimes in the case of alternators, recharging batteries. You're forcing chemistry with electricity. Okay, this case we're creating electricity with chemistry. So my next video we'll talk about non-standard conditions and what we can use these for.